Hi everyone, thanks for coming so early to the TVM tutorial. So hopefully you'll enjoy the day. Today I'm going to briefly tell you about what is TVM, what is our original motivation, and then there will be more specific tutorials about each specific element of TVM that you might be interested in. So before I start, let's start by what is the problem we want to try to solve in TVM. So as you know that we are in an age where AI and machine learning is really important. I myself come from a machine learning background, and the problem that wakes me up in the morning is always how I can build solutions to make better AI solutions and better machine learning run faster on all kind of hardware backends. So the goal of TVM is how we can build solutions, both training and inference and other solutions that allows us to deploy models, image recognition model, natural language processing, speech recognition models, and other models effectively on different kind of hardware backends. How I started to work on this problem, though, is quite interesting. So 2 years ago, I was working on machine learning. I have no idea on whether I want to work on compilers and so on. And then Thierry, my friend, came to me. He will give a talk about VTA later, to say that, hey, Tianqi, I'm starting designing this new deep learning specialized chip design. Do you want to work together? I said, sure. Seems that, at that time, actually, TPU didn't came out, but we kind of suspect that machine learning acceleration should be the future. How do I put my favorite puppy detector on top of that? And then he gave me this entire menu of microassembly instructions on, hey, here's how you can write assembly code to code my accelerator. So the gap between these high-level languages that I like to write, like Python, and the low-level hardware assembly interface kind of strikes me in a sense that it's really hard for us to actually work together and really put all these awesome machine learning models on the awesome design that Thierry had. So more broadly, as we start looking at TVM and thinking about problem, we find that there are a few key problems that different people want to address. For example, like a machine learning researcher like myself, always like to design new variants of models. You can find that there are new models in computer vision, NLP coming out every month or even every day. And you want to quickly try out and see how fast they deploy on your hardware devices. As a system researcher, some of my colleagues are looking at how we can perform different optimizations, system-level optimizations, like optimizing GPU backends, change data layout, distribute them on different hardware devices to really make things run fast on different kind of hardware backends. And computer architects like Thierry likes to ask how I can, I want to design new accelerators, but I don't want to spend another most significant amount of time actually writing test cases and show that my accelerator actually can support the latest requirement of machine learning researcher. Right now, there's a mismatch in a sense that it's really hard for us to do benchmarks on those newest models because the machine learning researcher write those models in Python, while if you want to design your newest micro accelerators, you have to write assembly code. How do we bridge that gap? So I think different persons have different kind of problems they want to tackle. And for many persons, it's not only one of a problem, it's usually multiple of them. For example, I, as a machine learning researcher, collaborate with computer architects, so we will want to ask questions like, how can I design new model variant that works well for a specific type of architecture? So before I get started, I would like to do a quick survey on, how many of you are interested in the first problem, deploy new model variants in your target? Okay, a few of you. How many of you are interested in system-level optimizations? Okay. How many of you are designing new hardware devices? Wow, that's a lot. Okay, not surprising why in this case. Okay, so you're going to hear it all. And I think one of the important lessons we learned is that even if you are working on one of the problems, you should not restrict yourself to one of the domains, because one lesson that I learned when talking to Thierry is that we keep pushing back and forth about what should be put in the hardware or the architects and what should be put in the software. And sometimes you want to make that trade-off and really gives you a design. And Thierry will tell you more about that. So this is the agenda of today's talk, not including mine, but here are the folks who are telling you the specific details of the talk. And they are, first of all, we'll have a talk about high-level programming languages, Relay, which is how you can do high-level system optimizations. Then Eddie will tell you about how we can use automatic machine learning to automatically optimize the workloads to reduce the amount of engineering resources you will have to support your hardware. After the break, Thierry and Luis will tell you more about how do we improve the hardware design cycles. Thierry will tell you about VTA, and then Luis Vega will tell you about how we can do actually cycle-accurate code simulation with your Verilog and Chisel design with TVM. And then in the afternoon, our friends from Amazon will give a guest talk about how they are using TVM to actually improve their production pipeline. Then we'll have talks about micro TVM. If you're interested in IoT devices, RISC-V, and microcontrollers, this is a talk that you should definitely pay attention to. Then Megan will talk about how do we do low-bit, 1-bit, 2-bit neural networks effectively, and that's also very important for edge devices. And then finally, Gus will give a talk about how we can bring in new data types like fixed point, posits, and different variant data types to TVM. As you can find that we have a spectrum of talks that ranging from high-level frameworks to a low-level hardware. The advantage of TVM is really we bring an ecosystem so that you can innovate in all those areas, and the combined power really gives you more accelerations by combining everyone's effort together. So my talk will briefly tell you about what is TVM and why do we want to use TVM. And then I will dive into a bit details on how do we do machine learning-based optimization. And it also serves as an introduction to many of the talks and tutorials that we'll hear about later. So let's start by why do we want to use TVM for your applications. As you know that if you want to work on machine learning, the first thing you'll hear about is TensorFlow or PyTorch or MXNet or other frameworks. And these are the frameworks that comes before deep learning compiler like TVM. And one natural question is like, why don't you just adopt those frameworks? That's not a surprising question. Actually, I myself actually worked on MXNet. I'm one of the main creators of MXNet. And I will tell you why I started to not abandon MXNet, but create TVM as a complementary solution to MXNet. So if you look at MXNet, TensorFlow, and PyTorch, and other systems, all those current learning systems are systems that tries to enable machine learning to make sure machine learning runs fast. But one of the untold story about those systems is actually, you need to spend a lot of engineering effort to build and optimizing those systems. If you go and talk to TensorFlow team, PyTorch team, or even MXNet team in these different companies, there are definitely more than 8 people that I draw here that spend their full-time effort optimizing those systems. And I'm telling the truth because I'm among one of them, and I spent my 3 years, my PhD, actually optimizing MX and other learning systems. However, this is really a hard problem for academic researchers, even startup companies or even big companies. For example, as academics, if I build a new chip, I cannot really hire another 8 engineers to help me write software for my hardware. So our question is, can we automate this process? Can we speed it up? More specifically, since we are talking about machine learning, and machine learning is so powerful, can we use ML to instead optimizing those systems we build? And that is one of the original motivation of TVM. And we start to adopt a new paradigm called learning-based learning system. The idea is that we want to use machine learning to optimize those systems, and as a result, we can spend less engineering effort to build those optimizing solutions. And specifically, when we are facing, our goal is we want to deploy machine learning onto all kind of hardware devices, including your CPU, GPU, mobile devices, and specialized accelerator. And there's a huge gap between these two. So before we talk about why do you want this kind of automated solution, let's take a look at what existing deep learning frameworks do. So nowadays, if you want to build a machine learning framework, you want to build your own hardware and support, say, MXNet or TensorFlow on your hardware, what you need to do is you want to represent those high-level computations in what they call a high-dimensional data flow graph. And each of the high-level data flow graphs, each of the node corresponds to a high-dimensional tensor operation, such as like convolution 2D or matrix multiplication. In order to offload those operations onto low-level devices, each of the nodes have to be implemented by a low-level library. In the case of NVIDIA devices, it's CUDN library. So what's the problem with this approach? The problem with this approach is that for each of the colored node here, they have to be implemented by a low-level hardware library. That means that there are definitely more than 3 people. As a fact, NVIDIA have a dedicated team to go and optimize CUDN libraries. The problem with this approach is that as you can find, machine learning is a fast-evolving field, And you can find that, another cases you want to do different kind of system level optimizations. As we can see, there are a lot of people interested in system optimization here. For example, you could take two operators and fuse them into one new blue node here. And usually that will give you faster speed because you reduce the amount of round trip to the global memory that you have. The problem is now that the blue node is a new operator that is not existed in the CODN library. So what do we do? One approach is you try to hire another engineer to add that, but you need to pay that money, and usually you need to wait for another month or like a few months. In the case of NVIDIA, that's a case where we asked NVIDIA to implement a new operator and they didn't add it until a year later. So that's a huge amount of turnaround time. And if you want to multiply that by new hardware you support, if you are a computer architect, you want to try new hardware every day, you cannot hire another team of engineers every day to actually build software for you. So we really need an alternative solution that replaces this engineering-intensive process. That's why we use TVM, a learning system approach to replace most of the human engineering effort for high-level optimization by a machine learning-based program optimizer that optimizes both high-level programs and low-level hardware. And specifically, let's come back to why do we want to use TVM. As I mentioned, that one of the most important factors that TVM have a machine learning-based automated solution. You will hear a lot about it today. That gives you that is intelligent and most importantly delivers state-of-art solutions that runs faster, as you will see, than many of the existing frameworks can offer. Secondly, TVM is product-ready and accessible. It means that if you are building a product pipeline, you can directly deploy TVM already on all kinds of platforms. We have examples like Amazon, Facebook, and a few other companies deploying it. But if you're also looking for quickly prototyping and doing research, it's also very accessible in a sense that you can prototype all the compiler transformations, optimizations directly in Python before you harden that into C++. And finally, TVM is a full-stack approach and extensible approach. That means that it's not only a solution for compiler, it's a solution that jointly combines model optimization, compiler optimization, code generation, and the hardware design, so that you can hack across the stack and try to innovate across the stack. Okay, so I've talked about why do we want to use TVM. Hopefully you are kind of convinced that TVM is the way to go. Let's talk about the specific details, and specifically how we can use TVM to build, how we can build machine learning solutions to actually speed up this process. So for each of our high-level computations in the color node here, what we do is that we want to actually accelerate it and doing automatic code generation. So in order to do automatic code generation, we'll represent high-level computations using a low-level specification language called tensor expression that describes how do you specifically compute each element of the tensor. Then for the high-level, for the tensor expression, we want to define a search space of possible program optimization that will give you different low-level program variants. To give a sense of what are the example low-level variants you can generate, for example, you could generate vanilla for loops that implement this dot product. If you are working on CPUs, you want to tie a loop a bit so that it gives you better memory locality. Or if you are working on specialized accelerators, you want to map some of the region of your code into accelerator intrinsic that's supported by your accelerator. So at a high level is that we want to build a combination of search spaces that contains billions of possible optimization choices, and then want to build a solution to automatically search over this space, so gives you the best operators for your specific machine learning workloads. Specifically, if you want to formalize this as a machine learning problem, you can use E to denote the tensor expression and S of E to denote a search space. Our goal of AutoTVM is to find a program configuration that you can send to a program generator, and then you want to measure the program runtime. Our goal is you want to minimize the program runtime. You can also define other objectives you are interested in, for example, energy or other cases, or memory size of a code. As long as it can be defined by the objective function, we can use this method to optimize it. And there are several ways to do the optimization. Eddie will tell you a bit more about it. The simplest ways you can try black box auto-tuning. The problem of this approach is that it really takes a lot of time to try things out. And another way is you can try to define a cost model that try to learn to predict what is the runtime of that, and you use a cost model to pick the best solution. One question here is how we can design an effective cost model for each of the configurations and each specific hardware. TVM's approach is we adopt machine learning. The idea is that AutoTVM will use a machine learning-based model that try to collect data from target hardware profiles and use that as training data to learn the statistical cost model that we can learn to use to guide the search. The advantage of this approach is that the machine learning-based model will automatically adapt to the hardware type that you are interested in and do performance modeling for your specific type of hardware without having you to worry too much about, how do I do modeling for my hardware. And there are several ways that we can use to design a cost model. Eddie will tell you more about it, so I will skip this part of the slide. But the takeaway is that we want to try to build cost models that are program aware. So the idea is that we want to try to build machine learning models that takes information from high-level programs and try to effectively predict the low-level performers that is aware of the program structure, like memory reuse, cycle count, and so on. To give you a sense of how much performance gain we can get by using this machine learning-based optimization approach, here's one example of one layer of ResNet workloads on Titanqi devices. Our baseline is, so the x-axis number of actual experimental trials that we can try to throw the experiment on a target hardware, and y-axis is the relative speed up over the baseline, in our case, CUDN library. If we use like black box auto-tuning, you can find that AutoTVM can find reasonable solutions that are kind of quite competitive to the CUDN baseline. But if you use machine learning-based approach, you can find that AutoTVM can find not only faster solutions than CUDN, but also it can find a solution better. The intuition behind is not really that machine learning model is better than human. It's really because machine learning model is able to specialize to each specific workloads that you care about, while humans, they need to derive a general kernel that works for all cases, while in machine learning, you can spend the time to actually optimize for specific workloads you care about. Another important thing that we do is we do transfer learning. I think Eddie will also tell you more about that, so I will skip this part. But the idea is that if we do transfer learning models to make use of historical data, actually it will give you even faster learning time and getting the better kernel faster. So the combination of all these techniques will bring us a solution that automatically learn to optimize tensor operators. And we have a nearest paper this year that describes the solution. And more importantly, we have an open source solution that allows you to also try out your own ideas. One of the purpose of this tutorial is not only to show off how good TVMs are, it's most importantly, I think, is how you can use TVM to accelerate your research and production. So we built a solution called Device Fleet that allows you to automatically experiment automatic program optimizations using AutoTVM. The idea is that you can plug in your experiment solutions, your method, in the AutoTVM experiment component in the Python side, and we're able to decouple that, and you can send that to a remote device that includes Android phone, the Xilinx FPGA, NVIDIA device server automatically, and you will be able to quickly experiment all this. And this is a very important infrastructure, for example, if you want to optimize for mobile devices and other kind of hardware devices you care about. And this is a real device fleet in action in our lab, and you can set up one of yours in your lab as well if you are interested. I know that there are a few industrial collaborators here setting up their own device fleet in-house. Okay. I've talked about the learning-based component. Let's talk a bit more about how we can build the system stack that combines with the learning, that can be combined with the learning-based optimization to give you the best performance. Well, as much as I would love to say that all machine learning-based automation can solve all the problems, actually this is not true. AutoTVM is one important component of the bigger end-to-end stack of TVM. So today you are going to hear more about each of the components, including AutoTVM, Relay, and Vita that Thierry will talk about. I'm going to tell you a bit about how do we construct the tensor expression optimization search space in here. So to recap, in order to build an effective code generation solution, we want to represent the high-level computations of workloads using tensor expressions. And by borrowing ideas from image processing language Halide, we try to define a search space that tries different possible mappings from tensor expression to low-level hardware program variants. One of the key problems they want to solve in deep learning workloads, though, is that how do we define effective search space that covers all the possible optimization that user might write so that you really get a state-of-the-art solutions that is better than the current existing operators that human might write? TVM is the first framework that's able to do that. It's really because we define a rich amount of search space combined with the machine learning-based optimization that gives you better solutions than what the frameworks can offer. For CPUs, actually, we can reuse many of the existing techniques in CPU optimization, including loop transformations, cache locality, and other optimizations that Eddie will also touch on. But what's more interesting is how do we support GPUs and TPU-like specialized accelerators. So for GPUs, one of the important things, we want to build primitives that's able to make use of shared memory so that we can do cooperative memory fetching to the shared memory so that we can reuse many of the shared memory workloads. And perhaps most exciting thing is how can we enable specialized TPU-like accelerators? These accelerators are special both in terms of their compute primitives they offer, as well as memory subsystem they have. In terms of compute primitives, many of those operators contains high-dimensional tensor operators. So if you look at CPUs, each of the programs that we write, we only have to specify how do I compute each element of the computation. These are usually most expressive because you can write scalar programs at your will. If you work on CPU devices, you know there are like AVX512, a neo instruction that allows you to compute things in vector order. And that really means you have to transform your program to be able to use those vector instructions. What's special about TPU-like accelerators is that those accelerators expose basic primitives as high-dimensional tensor operations. For example, you will have matrix-matrix operation in TPUs. In some other devices, you have matrix vector, or like each of them will have different memory layout, and the size of computation is going to be different. So the question is like, how can we build an effective compiler solution, a system stack that can target possible future tensor accelerator variants? You cannot really enumerate all the possible high-dimensional tensor operations because of the dimension and different size combinations. The solution that TVM have is that we will use the same tensor expression language to describe the hardware interface. The idea is that since we cannot enumerate all the possible hardware ISAs, let's try to build a DSL that allows us to declare the semantics of hardware ISA. And then we'll take the compute specification and hardware ISA specification and try to compose them together through a tensorization process so that can mix, match, and verify certain regions correspond to the corresponding hardware intrinsics. And then we can replace that certain region by using the hardware intrinsics that we support. Thierry will tell you more about how we do that in the VTA specifically. Another interesting thing about hardware devices is that you really need to explicitly manage all those memory buffers. And sometimes, when I started to work on accelerators, I learned that computer system is not only about DRAM, registers, and other things. You have to have special buffers for that you can then input to your matrix multiplication unit. This really makes things more complicated, and it really means that our system need to be able to support explicitly managed memory hierarchy, and TVM provides solutions to do that. And Thierry will also tell you about how we can do effective solution to hide memory loading latency, which is really important for those specialized accelerators. To recap, we want to build a combination of search space that contains both existing primitives for CPUs as well as new primitives that we introduced to really enable GPU and TPU-like accelerators. By combining that with AutoTVM, we can find state-of-the-art solution on those deep learning workloads. So to give you a sense on how effective TVM is so far, here's one of the end-to-end inference benchmark on NVIDIA GPU. And we are comparing against the state-of-the-art solution, TensorFlow and MXNet. I'm not biased because I built MXNet. So hopefully, I'm kind of convinced that's a very, very competitive baseline. Both of them are using the CUDA library written by NVIDIA engineers. If you use TVM, you can find that TVM can get you better solutions. If you look at standard models like ResNet, TVM is already doing quite competitive. But the most exciting thing for me is if you look at far right. So this is deep Q-learning model. You can find there's a 3x gap between the existing frameworks and TVM-based solution. So why there's a 3x gap? So by the way, deep Q-learning model is the model that used by DeepMind to play Atari games. So you can argue that maybe playing games is not as important as recognizing dogs, which could be true. But you can guess what's happening here. So if you look at the ResNet is a standard benchmark that every company who is working that's working on deep learning tries to heavily optimize for it. So you know that most engineers, when they are doing manual-based approach, they are focusing their effort on standard benchmarks. But if you go and talk to your researcher friends, go and talk to your industrial partners, they will tell you that they want to deploy something different than standard benchmark. For example, they might want to deploy ResNet with a bigger input image size if you're working on a self-driving car. They might want deploy different variants of models. And usually the standard libraries that are optimized for those standard workloads are not well optimized for those new models. While TVM's automatic machine learning-based approach is not biased against certain models, and it's going to tirelessly optimize each specific operators of the new model for you. That's why TVM is already adopted in many of our production pipeline here, because the machine learning-based solution really gives you a huge advantage when coming to supporting new models that people really need. Another exciting thing is that you can take the same solution and use it to optimize for different hardware devices. For example, here's a benchmark that optimizes TVM on ARM CPU and ARM GPU. And we are comparing against the state-of-the-art bench frameworks, TensorFlow Lite and ARM Compute Library on these platforms. One interesting fact you notice that when we switch to ARM CPU, our baseline is no longer TensorFlow, it's TensorFlow Lite, a specific new framework built from ground up for these type of devices. While you can adopt the same TVM solution, use machine learning-based specialization to specialize to those devices without building a framework from scratch. So far I've told you about results in CPUs, GPU, and mobile GPUs. What about accelerators? Actually, we built a new open source accelerator Vita in-house that contains open source microarchitecture, open source IC, and open source drivers that directly connects to TVM. And if you don't have FPGAs, it also runs on a simulator on a laptop. And Thierry is going to show you how you can do that today. And there are several innovations that I will let Thierry to tell you more about it. So one of the things that we are very proud of is that TVM is an open source effort that not only that started from academia, but now really gains a lot of traction in the industry as well. We get more than 221 contributors from different companies, and TVM is already used in production in the cases like Amazon's deep learning compiler services. They will tell you more about that today. And Facebook is using TVM to optimize their mobile and server workloads, and there are more to come. We are building an open source community that is governed by the community. The idea is that although we started a project, UW or Sample or myself do not own the project. The idea is that everyone who contributes to a project actually will have a say on the project, and we are promoting people to commitorships by their contributions. So far, we have more than, I think, around 20 committers. And if you are interested in contributing to TVM, you are more than welcome to become one of us to influence the direction of the open source project. And we really believe that it's really important to have an open environment that everybody can contribute and work together so that it works for your own research. As a researcher, one of the most exciting things for me is that TVM not only enables new production pipelines in the industry, it also opens new research frontiers. For example, Jerry is going to tell you about how we can do high-level differential programming using TVM. And Thierry will tell you more about Vita and how we can use TVM to do new architecture research. Team in Berkeley is using TVM to build their in-house trusted enclave solution so you can run machine learning on a secured enclave and provide you privacy and protection. And as I mentioned, we are building a machine learning-based solution to optimize your programs and hardware in the future. And TVM is really a nice test bed that allows you to try out different machine learning methods to optimize those programs. As a result, as Luis mentioned, we started a new research group called Sample, and we had an annual conference. We just had one last December, and we're expecting to have one this year, so you are more than welcome to join us as well. So I've talked about, so far I've talked about what is TVM now, and there are a lot of effort ongoing in the community as well as at Sample Group on pushing different fronts of TVM. This includes supporting more training support and automations that allows us to do a better quantization model, automated hardware design, and so on. And we are also moving the hardware design to support Trizzle and more FPGAs and as well as ASICs. Okay, to summarize, TVM is this end-to-end stack. You're going to hear more about different part of the stack today. And the reason that you want to use TVM is because TVM have these three characteristics. It's intelligent and gives you the state-of-the-art solution on not only the standard benchmark models, but also the emerging new models that you care about. It's product ready, but also it's accessible. That allows you to do different kind of high-level researches using Python and the deployment runtime they have. It is full stack that allows you to hack across the software, the model, and hardware design to really allows you to do researches across the stack, which is really exciting. And without further delay, I will actually I will answer a few questions if you have, and I will hand it off to other awesome folks to hear more about TVM specifics today. So I'm the only talk who don't have IPython notebooks, and Jerry will get you more prepared and get your hand dirty on the specific details about TVM. But before that, if anyone have questions, I would be more than happy to answer them. Okay, so I guess I will hand off to Jerry.
Right there.
There's one round. Yes.
I'm curious, you benchmark on Python X, did you also benchmark on later generations like V100?
I see. Yeah. The question is like, did we benchmark the latest Tensor core enabled hardware that we have? The answer is that so far we have not yet supported Tensor core Tensorization, so we have not yet benchmarked on V100. But on the other hand, we do have latest benchmarks on the 8-bit enabled hardware devices on NVIDIA devices against NVIDIA's in-house solution TensorRT. If you go to tvm.ai, there's a blog post describing that, which we believe is very exciting. You can find that TVM is very competitive to the NVIDIA's best ever TensorRT on ResNet, but we can really get better performance and enable models that TensorRT did not support in-house. And more importantly, TVM is a full-stack open-source solution, so you can go and tweak it, while the TensorRT is a black box solution that NVIDIA offers. Okay. So next, Jerry will talk about the relay, the high-level deep learning AI